Hey everyone, I'm Anish, and in this video, Tushar and I will be presenting on MambaFoley, which is a novel approach for generating Foley sounds using selective state space models. So let's talk a bit about the problem that MambaFoley is trying to solve. Foley sound generation involves creating sound effects that are precisely synchronized with visual media, such as films or games. Traditionally, Foley sound creation is a labor-intensive process that requires manual synchronization of sounds with video. This can be time-consuming and costly. While automated methods exist, they often struggle with issues like maintaining temporal coherence, managing high computational costs, and accurately controlling sound timing. One of the key previous works addressing Foley sound synthesis is T-Foley, which is a controllable waveform domain diffusion model for Foley sound synthesis. This model focused on generating high-quality Foley sounds with precise control over timing. It introduced a temporal event feature allowing users to specify both what sounds to generate and when they should occur. T-Foley uses a unit-based architecture with an autoregressive bottleneck, using LSTMs at its core to model audio sequences. T-Foley's temporal conditioning is achieved using block film, which reduces computational complexity while still providing precise temporal alignment of sound events. Block film allowed T-Foley to accurately represent the envelope and timing of sounds, which ensured realistic audio sequences.
Another key previous work for the MambaFoley architecture is the integration of a selective state space model. State space models are mathematical frameworks that are used for modeling systems that evolve and change over time. In an SSM, the state space represents all possible states a system can occupy, and the model tracks how the system transitions between these states based on input sequences. A selective state space model, like Mamba, enhances traditional SSMs by introducing dynamic, content-aware mechanisms. Mamba adjusts key parameters based on the input, allowing it to selectively focus on relevant information while ignoring unnecessary details. This flexibility enables Mamba to adapt its internal state to the input sequence, similar to attention mechanisms in transformer models. These innovations make Mamba more effective for tasks with long-range dependencies and complex sequence modeling, matching or even surpassing the performance of other advanced models while remaining efficient. Now, let's introduce MambaFoley. It combines a diffusion-based model with selective SSMs to generate Foley sounds with accurate timing and high fidelity. This combination of the two model types addresses the challenges of generating temporally coherent audio sequences, making it an important advancement in the field of sound synthesis for multimedia applications. Building upon T-Foley, it's able to achieve the accurate timing and high-fidelity sound in the sounds it generates, and is able to do that more efficiently than traditional LSTMs or attention mechanisms, which are used at the core of T-Foley.
MambaFoley takes in two main inputs: sound category labels, such as footsteps or a dog barking, and temporal conditions that define when and how often these sound events should occur. Specifically, the dataset used to train MambaFoley only includes 7 different sound categories. The temporal conditioning is a result of taking the root mean square of the waveform of some real audio sample belonging to the same sound category. The model itself is based on a unit structure similar to T-Foley. MambaFoley uses G-blocks, which consist of sequences of 1D convolutions for downsampling and transposed convolutions for upsampling. The G-blocks contain the film and block film layers to incorporate the categorical information and temporal information respectively. The bottleneck contains two parallel Mamba blocks, processing audio sequences in both forward and backward directions, improving temporal accuracy. This is how MambaFoley utilizes the capabilities of SSMs to process audio sequences. The outputs of the two parallel Mamba blocks are each normalized using root mean square layer normalization, and then concatenated and processed by a single linear layer.
MambaFoley, as well as T-Foley and Attention Foley for comparison, were trained using the Foley Sound Synthesis Challenge dataset, which consists of 6+ hours of audio spanning 7 categories, including human and nature sounds. The dataset is divided into training and test sets, with 100 samples per category in the test set. The models were trained for 500 epochs using the Atom Optimizer, incorporating a variance-preserving cosine scheduler and classifier-free guidance to improve sample diversity and add robustness. The models process audio features in small time windows, and the sneeze-cough category is excluded to ensure fair comparisons. Frechet audio distance and EL1 distance were used to evaluate the realism and temporal alignment of the sounds generated by the models. MambaFoley outperformed the baseline models in terms of FAD, showing a similar performance in temporal accuracy. In a subjective evaluation involving 20-plus participants, MambaFoley was perceived as superior in overall quality, and for temporal fidelity, MambaFoley performed comparably to AttentionFoley, with all models appearing similar in this aspect.
MambaFoley successfully automates high-quality Foley sound generation with precise temporal control, utilizing SSMs and block film for efficient processing of long audio sequences, instead of relying on transformers or LSTMs. It outperforms traditional models in terms of realism, timing accuracy, and computational efficiency, making it a promising tool for multimedia production. Additionally, MambaFoley has a potential for further development in real-time and multimodal applications.